Stefan Kloster. Going to talk about longwave. Multi-time integrator for longwave shallow water equations.
Okay, thank you for the introduction. Yeah, this is not anymore about mimetic time integrators. I introduced one word into my title, multiscale, and there I just want to stress that the scheme I present is, has some multiscale behavior, and that I think is or should be stressed a little bit. I did this work together with Rupert Klein from Freie Universität Berlin, and yeah. So, whoops. How does it go to the next slide? How does it work? Oh, okay. Yeah, it was already said that, here we go, that we have a very stiff system for the atmospheric flows. We have sound waves, internal gravity waves due to buoyancy, and also the snow Rossby waves. And in between we have a scale separation. Well, when we want to numerically model it, we either have to use reduced equation sets where these fast waves are filtered out, or we have to do some, for example, semi-implicit or implicit discretization. Here I take the root of a semi-implicit discretization, and the overall goal is to develop numerical or numerical integrators to model global global phenomena with high resolution. So we would like to keep the sound waves, which are resolved by the scheme, but we want to filter out all the waves which cannot be reproduced by the numerical scheme, because they are not anymore or they cannot be represented by the large time step anymore. At the same time, we would like to consider source terms. So we have balances, for example, for cloud formation and the release of latent heat. This introduced some small local divergence and the send out of acoustic waves. And we are not interested in the acoustic waves, but we are interested in the underlying balance. And that should be also reproduced on a more local scale by the scheme. Yeah, so this is the motivation of the scheme. And first of all, I want to talk a little bit about the equations I look at and classical discretizations. Then I introduce the multilevel method for first the linearized shallow water equations. And in the end, this method is introduced into a semi-implicit scheme for the fully nonlinear shallow water equations. Okay, I do this study for the shallow water equations, so not for the full atmospheric flow equations, compressible ones. Here we only have external gravity waves, but these are the equivalent of the so-called lamp waves in atmospheric flows. And the goal is to model these, or at least the fast inertial or the long wave gravity waves in a good way while minimizing the dispersion error. And I also talked about these source terms and the small balance or the balances we want to maintain by the scheme. And this is modeled here by a bottom topography which is time dependent. Yeah, so this might be somehow a little bit unusual. Okay, let's first look at the linearized version of the shallow water equations, and let's do a multiple scales expansion to see what really happens in the regime of interest. And here I consider a multiple scales expansion with two space scales, one normal space scale and a large space scale. And this is why we want to model long wave gravity waves or sound waves. And on the other hand, we want to have these small scale balances, which is modeled by the topography. When you do this asymptotic analysis, you get the following result. For the height, you have at leading order, it's just time dependent, and it's the evolution is given by the mean evolution of the bottom topography. In the next order, we have a height which is only dependent on the large space scale. And this evolution is just given again by the linearized shallow water equations, but without any source terms. So we have free propagation of long wave gravity waves. On the small scale, however, we have the small scale balance between the bottom or the evolution of the bottom topography and the divergence of the velocity. And the next order height is some kind of Lagrangian multiplier, or takes the role of that. What does it mean for the numerics? So the goal is, on the one side, to remove freely propagating modes which are under-resolved in time by the scheme. But we want to minimize the dispersion relation for resolved or also marginally resolved modes. For the small scale, we want to correctly compute the the dynamics which are given by the source term, so the balance. But we don't want to have any resonant effects for which are produced by these acoustic waves, for example, or gravity waves which are induced by the time evolution of the bottom topography. And everything should be done in with second order accuracy. Okay, let's first look at at two classical schemes, which is the implicit trapezoidal rule and the BDF2 scheme. And when we so here we have a first test case with which is a simple wave, right-running simple wave with long wave data and very small scale data. And the red line is the numerical solution, and there's also a black line which you do not see. This will be the exact solution. So if you run this test case for the trapezoidal rule, you see that the long wave data is advected, well, I would say okay. It has some dispersion, but the amplitude is at least is kept. But on the other hand, if you look at the small scale data, these data is essentially not advected, which is due to the group velocity, which is nearly zero, and you get a very wrong dispersion relation. On the other hand, if you look at the BDF2 scheme, you have a very different behavior. The small scale data is nearly immediately filtered or filtered out, but for the long wave data, you have some kind of damping, compared to the trapezoidal rule, and you also have more dispersion. Yeah, when you now look at the problem of balancing source terms, I have here a setup where you can see the height and the evolution of the bottom topography, and the red dashed line is the solution or the leading order asymptotic solution. So the goal is that the height should come up to be nearly the same as the asymptotic solution. And when you look at the trapezoidal rule, you see that this is not really the case. So the numerical solution is oscillating around the asymptotic solution, and the balance is not really attained. But on the other hand, if you have a look at the BDF2 scheme, the balance is very nice attained after only a few time steps. And this is for this test case, we have a CFL number of 80, and the test case before was for a CFL number of 10. Okay. This can be also seen from essentially from the dispersion relay or discrete dispersion relation of the schemes. So here we have the frequency wave number relationship, and the black line is the dispersion relation for the exact equations, and here the red line is for the trapezoidal rule and the BDF2 scheme, and also we have the amplification factor, and we can see that we have a better dispersion relation for the trapezoidal rule, and on the other hand, the amplification factor is such that we have for the trapezoidal rule, we have no damping, but for the BDF2 scheme. And this behavior is further amplified if you go to a higher CFL number. So this is for CFL number 10, and also we have a change of scale. So this is just 1/4 of what we had before in wave numbers. Okay, what do we learn? So on the one hand, we had the desired properties that we want to minimize dispersion for resolved modes, and also preserve their amplitude. For this thing, the trapezoidal rule was very well. But so the balanced modes, and also for freely propagating high wave number modes, the BDF2 scheme was better. So now we look for a strategy to combine these two aspects into one single scale-dependent time integrator. The key ingredients are a quasi-spectral decomposition of the height and velocity, which can be given by some projections. Then we have two different time discretizations. In our case, I consider the trapezoidal and the BDF2 scheme. And what we do then is that we consider a convex combination of the two schemes with some scale-dependent weights. By doing this, we get another new operator, which has some kind of multi-level or multi-scale information. So these operators actually represent the Helmholtz operator for the two schemes in the particular case. And by the scale-dependent blending, we get another Helmholtz problem for the height in the end, and also similarly for the velocity. We get a scale-dependent update, which has to be solved again, or this time. Here for the trapezoidal rule and the BDF, or the blending of the trapezoidal rule and the BDF2 scheme, looks like that. This is the Helmholtz operator for the trapezoidal rule. That's a mistake here. Anyway, in the linear case, it's the same. Also for the BDF2 scheme, and when we blend this on each scale, we get such an operator. So we still have to solve a Helmholtz problem on the finest scale. We just have a scale-dependent Helmholtz operator. Okay. Yeah, then we have to do or define the scale the scale splitting of the height and velocity. For the height, we just use common multigrid prolongation and restriction operators. So this is a full whitening and the linear interpolation, which we use here. And the scale splitting is defined such that for the causes grid level, we use just what we get when we restrict to this level. And then for the next finer levels, we always take the difference between the causa level, what we already had, and what we get for additional information on the next finer level. For the velocities, since I consider a staggered grid approach, I cannot use the same splitting operators. And it turns out that here the velocity has to correspond with the height gradients. And it turns out that we get some other stencils for restriction and prolongation, which are given here in this picture for one dimension. So this is a front point stencil then for the restriction. And, well, how does this scheme work? So here I have, again, this multi-scale test case, and I have also plotted by this black dashed line. That is the solution of the trapezoidal rule, but just with a long wave data. And if you look at this, you see that you essentially get, for the long wave data, you get the behavior of the trapezoidal rule, but at the same time, the high wave number modes are filtered out. In the other test case, this is one with a source term. You see that the balance is also attained only after a few time steps. So now, oh yeah, and then I tried to get a dispersion relation for the multi-level scheme, which is not so easy actually, because the eigenfunctions are not the cosines and sines, as this is the case for the trapezoidal rule and the BDF scheme. And so here I just did it numerically and using these sines and cosine functions. And so you see some artifacts here, which which are somehow strange. But you see when you look more at this part here, you see the overall behavior of the scheme. So for the resolved modes, we have more or less the behavior of the trapezoidal rule, but then for the higher wave numbers, the scheme turns or switches towards the BDF2 scheme. And also here we have the amplification factor for the resolved modes. It's more or less that one of the trapezoidal rule, and then you introduce some damping. Then I introduced the scheme into for the fully nonlinear shallow water equations, and here I extended a projection method for zero Froude number for flows by introducing the local time derivatives of the height. And this turns out that first in a predictor step, we have to solve some auxiliary system, which can be done in an explicit way using good enough methods for well, hyperbolic equations. And then we have two corrections. One correction here for the advective terms in our scheme, and which leads to one Helmholtz equation for a height correction. And then we also get the pressure gradient in a second correction, or at least an update for that, by solving another Helmholtz problem. And this is done in two different ways. Here, once by using a trapezoidal approach, trapezoidal discretization, and in a second time using a BDF2 discretization in the second correction. And these two schemes can be again combined into the multi-level method, which I presented for the linearized equations. And by this you get this again a multi-scale or multi-scale method, this time for the nonlinear equations. And you also can do some kind of asymptotic or multiple scales asymptotics, and you essentially get the same result as for the linearized equations. You just have some coupling between the scales. And if you now look at the results for balancing, here you see that with the trapezoidal rule you have a lot of oscillation around this balanced state. For the BDF2 scheme, the balanced state is attained after some time. And whoops. And for the multi-level method, we also see that the balanced state can be attained after some time. So to come to an end, I've motivated my scheme by the need of simulation of large-scale flows at high resolution. For this, I introduced a semi-implicit discretization for the solution of, here in this case, the shallow water equations. I analyzed some classical schemes, and by the outcome of this analysis, I introduced a multi-level method with a quasi-spectral decomposition of the data and using multi-grid techniques, and this was applied in the end to the nonlinear shallow water equations. And there are still some issues. For example, the efficient solution of this multi-scale or multi-level operator, then this was only done for now in one space dimension, and also it should be applied to atmospheric flows, where you can have a look at the poster of Tommaso Benacchio. Yeah, thanks for your attention.
Yeah.
So maybe this is on the poster, but I wondered, have you kind of on the site estimated how much of a problem this really is for the atmosphere? Do we really have divergent forcing at acoustic frequencies that needs to project, that needs to have an atmospheric signature? For example, small cloud elements might have latent heat release at a relatively short time scale, but does it really project that strongly out of the acoustic modes as opposed to gravity wave modes?
Excuse me, I didn't get you.
So my question is, the concern is that we have some forcing in the atmosphere that might really be in acoustic modes that we're going to miss if we use soundproof equations or we don't do something multi-scale, right? We don't want to just forget about forcing that properly belongs in the atmosphere that starts out at frequencies that are higher than, say, the Brunt-by-Solid frequency. So their forcing is faster than the gravity wave forcing. But I wondered, have you actually done some work to be sure this really does happen as opposed to just hypothesizing it might be a problem?
No, I haven't done this work. The hypothesis was to, on the one hand, to be able to model long wave acoustic modes, or also even gravity modes, but on the other hand, to filter out high wave number modes which cannot be resolved in time. But I haven't done any. Well, I'm a mathematician more, and so I'm interested in developing these schemes, and I cannot say how much this really matters.
We had a question from Thomas.
Yeah, so in your example, the short waves are fast. So what happens if you have short waves which are slow, like Raspberry waves?
Well, these should be resolved by the scheme, by the implicit scheme, so they should be correctly advected. I haven't got an example here. I can show you if you want to have. I have them on my computer. Yeah.
Do you use, it wasn't quite clear, do you use all this available dyadic scales in your multi-scale scheme, or do you just define a smaller number of scales? How many scales do you use in your multi-scale?
Well, in the end, you have defined this blending parameter.
Okay.
And there what I didn't say, we choose that we use the trapezoidal rule for all levels which have a grid CFL number of smaller or equal to 1.
Okay.
And then we nudge the discretization towards the BDF scheme. And then it depends on your initial value problem, for, where at which level you have the trapezoidal rule. And then really something happens in between this level and the finest level, where you use the BDF2 discretization, and but in between you use well, as many grid levels as you want. The only difference is that the next causal grid level has grid cells which are twice as large. So I do not introduce new grids.
Great. Why don't we thank Stefan again?